get into a topic like that?
I was very interested. I've seen certain things as far as what has been shown on certain documentaries. And then
Any documentaries or things you can mention?
it was a lot of things that were done by Dr. Stephen Greer.
Okay.
And a great deal of things. As a matter of fact, I hold the man in very high esteem. I feel it's very unfortunate that the UFO field seems to be so divided. It's almost as divided as the country is at this point in time. And I wish people were more unified. I've always been a person that drives toward unification of concepts, ideas. You can always work things out. You can always reach a compromise, always. And I think everybody benefits as a result. The alternative is the enemy wins. When we fight amongst each other, our strength is divided, is weakened. The enemy will always take strength from that.
So you're watching like Close Encounters of the Fifth Kind or Unacknowledged, things like that.
Absolutely.
How do these crafts
operate? How do they work?
How do they work?
And then they work.
So this patent is somewhat you kind of reverse engineering and how you think they work based on the observables and these sorts of
exactly. The whole idea is it can't all be Newtonian propulsion. You basically take something, you throw it out the back, and the thing moves forwards. The whole idea of the Newtonian third law of action-reaction can't all be Newtonian. What if there's non-Newtonian propulsion? So in other words, can we do something to the field that we operate in, the gravitational field, for example, to make objects have diminished inertia?
Yeah.
Since inertial mass and gravitational mass, after all, there is equivalence between them.
Right. So I have a dumb question, Andy. You publish a thing like this, and it seems like pretty well synthesized and researched. Why doesn't, presumably there are legacy programs, if you believe David Grush reverse engineering this stuff, why don't they immediately kind of hit you up?
No idea whatsoever. As a matter of fact, at one point in time, I almost expected to be contacted, so then the idea almost occurred to me, almost instantaneously, that they must have this somewhere.
They've already sorted.
That they have figured it out, and they already operating certain devices. And then I hear these things about reverse engineering craft, and then that thing bothers me because everything I've done is really based on Oliver Heaviside's version of Maxwell's equation.
Yep.
The four unknowns that electrical engineers have grown up to love and use. Thank God, because the original were absolute extremely
an unusual, unusable, mess.
Quaternion, formalism. My goodness, So again, the genius of Oliver Heaviside, and all you do, couple it with the harmonic oscillator, and certain things occur based again on resonance. Resonance is extremely important because it talks to energy amplification.
So you're implying that you don't believe in the sort of ET craft hypothesis. You think this is all sort of man-made,
or do you think you've just stumbled across the same physics of operation?
Yeah.
I believe that there's man-made tech and there's ET tech. It's possible the ET tech was reverse engineering from gifts or craft that were found, historical items, who knows where and how. And there's another avenue. There's man-made tech. Why can we have that kind of acumen, that kind of mind? You mean only these, they call non-human
intelligence?
Only NHIs can have this kind of intellect? Why can we?
Yeah.
I mean, we should take pride in who we are as Homo sapiens sapiens. We represent a certain intellect.
And this is an interesting question. Are there multiple branches, multiple tech trees that could be filtering their way through the defense intelligence space? Some of them approachably nuts and boltish from a technology that's a couple of hundred years more advanced than us, and then other examples that are far more exotic, that when you open them up, you see nothing familiar, you see nothing recognizable.
Absolutely. So in other words, there's man-made tech and ET tech, and I think you can tell them apart. The one thing that struck me based on what I came to understand from the idea of the superforce, if you take the gravitational field equations of Einstein, you can readily deduce that the superforce acting on the spatial temporal geometric structure, what we understand as a quantum vacuum, locally, can actually give birth, generate energy density.
Right. This is the idea of Robert Wheeler, the notion that energy density determines the shape of space-time or the shape of the quantum vacuum, and the quantum vacuum determines the propagation of that energy density.
And the superforce equation, which is really a re-rendering of the Einstein gravitational field equations, talks to this.
Right.
Talks to the. And then Bob Lazar mentioned at one point that it seemed to him that the so-called sports model was as if grown out of the vacuum itself. absolutely smooth, like a 3D printing out of the space-time fabric itself. The Superforce speaks to that directly.
Are you familiar with Ken Shoulders' work?
Of exactly vacuum objects. I've read certain papers as well.
It's very interesting, this idea of the vehicle being 3D printed out of the quantum vacuum, because we can't seem to quite understand exactly, because, when you talk about chemical vapor deposition, the manufacturing techniques associated with making very small nanostructured heterolattices. My graduate work, for instance, is in topological material physics. And so we do know more than is generally acknowledged about how to manufacture those lattices, but we don't have a lot of control over where exactly the atoms go. We just spit them out and physics takes over and it deposits them where it wants to deposit them in the lattice. So if you need them to be in extremely specific lattice points, and then you need to do layer after layer after layer to get these really novel behaviors, topological superconducting layers, topological insulative layers, Josephson junctions, and then one after the other. We don't know how to do that. So does that get 3D printed somehow?
Fascinating. Okay. Well, we're getting deep quick. I want to just for the mass audience, kind of lay some scaffolding, lay the groundwork. So you mentioned Heaviside. Most people now, when it comes to kind of classical electrodynamics, go off of Oliver Heaviside's kind of simplification of Maxwell's equation.
Absolutely.
So where is conventional classical electrodynamics off, where you think you've found kind of a different branch of Heaviside? Because most people adhere to it, right?
This is not anything new. This is not new physics. This is a new perspective on all physics. All I've done was taken the Heaviside version of Maxwell's equation, coupled them with a harmonic oscillator, and shown that you get nonlinearity with respect to the angular frequency, either vibration and or spin, because as you well know, the mathematics is heavily similar.
Right.
And come up with on the second conditions, you get resonance conditions.
So you get these
energy amplification.
Emergent phenomena. They're not immediately obvious
phenomena
under normal circumstances.
So let's break it down. What is a harmonic oscillator?
A harmonic oscillator, if you think of the best way to describe it is from Hooke's law, the whole idea of F equal minus K X.
A spring.
Exactly.
A spring oscillator.
Exactly.
That makes a sinusoid in XY.
Yes, sir. And then you just write, as you well know from Newton's second law, M acceleration, or M, the X double prime dt square. The whole idea of MA equal this minus kx. From that results your harmonic oscillator.
So we're talking about derivatives from differential calculus, and this is how you go from y equals kx, Hooke's law.
Extremely simple stuff.
For you, combining that concept with Heaviside.
From there, what happens is from a simple scalar, as a matter of fact, I send you what we presented to the patent examiner, and you can have that with the podcast. You can actually, sure, absolutely. That's been already presented. It's in the public domain, so it's considered non-governmental, unclassified
domain.
That's it. It's public domain. Since the USPTO primary examiner, a gentleman by the name of Philip Bonzel, has already has put it into the public domain. It was given to him via phone conversation. So that particular PDF was sent to him, and then we had a phone conversation with the Navier attorney, Mr. Mark Luth, which, by the way, was tremendous. In every one of the 5 patent applications, mind you, 3 of them became patents. The 2 that did not become patents are the ones that seem to be most mundane. The high-frequency gravitational wave generator became a patent. The high-energy electromagnetic field generator became a patent.
The most exotic concepts.
Yeah. Using an inertial mass reduction device became a patent. After some doing, of course, Mr. Philip Bonzel was extremely in awe of that. He said, this is not possible. I mean, neutron stars cannot produce this electric fields and magnetic fields. We're talking about electric fields on the order of 10 to the 18 volts per meter.
So how do we get to that? If you're combining the harmonic oscillator with the Heaviside stuff, how do you get to those, those that big of electric field size?
Again, it is in that PDF, and you can follow the math. It's extremely simple. But the whole idea is that you get, from the scaling analysis, you get a simple relationship that shows that it must be correct, because the electric field, that relationship, it gives you a relation. So the scaling analysis of the Heaviside version of Maxwell's equation give you a simple relationship for the electric field strength, E, and also one for the magnetic induction, otherwise known as the magnetic flux density, also known as the B field. Well, from those 2 relationships, you can actually see that E max divided by B max equals C, equals the speed of light, exactly what Maxwell showed. The whole idea.
Yeah.
So that must be correct. And when you couple the harmonic oscillator within those 2 relationships, you get something for the B field, which is amazing. It shows It shows variance with respect to angular frequency squared. So in other words,
That's interesting. So now I'm tracking, because in your patent you use microwaves inside the annular channel, and it's like you
to
called
vibrate.
it to vibrate the atoms.
Right.
You called it a confined photoelectric effect.
That's
and
exactly
what
what
I found
it is.
interesting is the high temperature superconductor patent is necessary for the high frequency gravity wave patent.
They speak
to work,
each other
because there's a high Q factor associated with the high temperature superconductor.
But for some reason, the patent examiner did not even take that into consideration.
Sure.
Exactly what you said, because then just by that simple argument, from an enablement point of view, he should have passed, or they should have passed the room temperature superconductor.
So what allows that frequency?
Dr. Viktor Lakhno, Russian, of the Russian Academy of Sciences, actually shows in his archive published paper. I've never been able to publish an archive, so the man must have, either known some moderators. Again, he showed that my room temperature superconductor from a mechanism point of view could work. And yet the patent examiner just refused to grant the patent. So
it was an incredible idea, because you describe what is a proximity superconductor, probably also a topological superconductor.
From someone that actually has that knowledge. Thank you, Jack.
Yeah. So encased in a ceramic. And so it's the interfacial layer that is superconducting. That's where the current moves. And so when you've got these 100 terahertz microwaves inside the annular channel of your triangle patent, it's exciting. And you're setting up that standing wave. And that's
what it's all about. Resonance.
The W squared term is why this blows up. Yeah.
That omega square is very important.
Yeah.
And for some reason, people refuse to see the mathematics speaks to the physics.
Are you worried at all about that huge B field and the surviving materials surviving it? Because
that's something we have to be aware of.
As you well Tesla fields,
as you well know, you have to be extremely careful, because usually when you go above 10 to the second, maybe even pushing 10 to the third Tesla, we're talking about tremendous
we've never even
yields on the
B field is a magnetic field measured in Tesla. We've never made a magnetic field any larger than 30 Tesla, 40 Tesla.
Usually
in CERN and gigantic electromagnets.
I heard of something up to 120 Tesla, but that's a rumor.
Yeah, and the Earth's magnetic field's like a thousandth of a Tesla, or 10,000
how
of a Tesla.
How would you insulate materials from that size of magnetic field?
You wouldn't insulate it. You'd use something that, this would all want to be synergistic. So you would want to use something that benefits in some way from exposure to that field, rather than trying to fight physics. I think that's where really brilliant engineering comes in, is that you're not going to put a bunch of things together that are parasitically affecting each other in negative ways, and you're trying to finagle your design space to make it work. You'd put a bunch of things together that actually help each other work better with their side effects.
Physics is not enough. The engineering of the physics trumps everything else.
Yeah.
Again, experiment trumps theory every time. And I believe trumps should become a verb.
Have you worked on this from an engineering perspective at all, or is it purely theoretical?
We worked on a high energy electromagnetic field generated experiment at NAVAIR. However, we weren't able to obtain an electrical charge of more than 10 to the minus 8 coulombs. We need at least one coulomb
on the skin
to show the Pais effect is correct. I call it the Pais effect, not out of hubris, as people would choose to call it, but because it was something purely original. And I decided, why not? Let's call it something that's never been called before. And there was one other Pais there, Abraham Pais, the autobiographer of Einstein himself, a great physicist of his own right. Said, okay, let's couple the names.
In the context of all we've talked about, would you step through your explanation of the Pais effect from a high level?
Absolutely. Okay. Usually I define it as controlled motion of electrically charged objects, usually from solids to plasma, based on accelerated vibration and or accelerated spin, giving rise to extremely high energy densities. Hence, electromagnetic energy fluxes. However, it can also be thought of as the generation of high energy densities based on certain vibratory fields of plasmas, cold plasmas. We're talking about plasmas that have been driven far from equilibrium.
Your xenon gas in the annulus that you kind of move it back and forth with your 100 terahertz alternating electric field.
The terahertz frequency is an interesting field that should be looked into. But again, we're not here to educate and enlighten the enemy, so that's as far as I go.
Well, it is interesting, how Puthoff has talked about these kind of micron layers, magnesium bismuth, and he says that they, micro-size waveguides for terahertz. And so
there's a reason. Look into the slide presentation that I presented at the 2019 AIAA SciTech. That presentation, please also post that in your podcast along with the patent examiner interview, those slides. It makes a lot of sense, but look very carefully, slides 4 to slides 9 in that particular presentation, and you'll see why the terahertz frequency is so important. It speaks something to that Dr. Eric W. Davis published in one of those DIA reports that I saw.
Teleportation.
More to do with a certain macro dimension,
A fifth dimension?
a fifth dimension.
Right. So there's I don't know how much you want to say, but there's a coupling factor between the electric field that you're setting up to generate high frequency gravity waves and this oscillatory behavior of the particles, which potentially polarizes the quantum vacuum and allows you, the analogy that I have used is, imagine you have a Ziploc bag that's full of water, but it's kind of sloppy. And you imagine you can push on it on one side and you set up a pressure gradient. So now you have the quantum vacuum doing work for you and pushing on you with its own pressure. And it has such a tremendous energy density, like 10 to the 44th, calories per cubic centimeter or something bananas, that it does an incredible amount of work.
So it's literally, this is based on metrical engineering. It's using,
It is.
and quantum electrodynamics, even Feynman would say, or whatever, the 0 point is full of energy. And
Absolutely.
It's used, and Hal Puthoff talks a lot about, polarizable vacuum that you can electrically polarize. And so it's using kind of creating a gradient basically to propel an object. Is that
Some of your work has cited Max Born, Paul Dirac, and
I
heavily Hal
talk more
Puthoff.
to the Schwinger limit, breaking the Schwinger limit. Why do I talk about that? Not just because I want to make black holes, but the whole idea is that when you put more and more energy into a particular space-time locality, you can actually unravel what we understand as continuum, space-time continuum within that quantum vacuum limit. The Schwinger limit, really, this whole idea of generation of particle antiparticle fields, this is exactly what the Schwinger limit needs. And it's on the order of 10 to the 33 watts per meter square, corresponding to an energy density on the order of 10 to the 25 joules per meter cubed.
Enormous amounts of energy.
Enormous. Speaking again to those electric field strength of 10 to the 18 volts per meter, commensurate to a B field on the order of 10 to the 9 volts per meter again.
What is the Schwinger limit?
The Schwinger limit truly, it represents how much energy density the quote unquote quantum vacuum, or rather space-time fabric, can withstand before it breaks apart.
And how does this impact the black hole information limit, right? Because you've talked about this.
I've never looked too much into the information loss paradox.
Summarize what you said for sure. So basically, what you're saying is you're using this electromagnetic amplification methodology
To create this energy density. Yes,
to essentially break the fabric of reality in a way that uses it as propulsion. Is that right?
that's 100% correct. Because once you form this black hole, I truly believe that every black hole, quote unquote, has a white hole. There's a wormhole that truly forms between whatever that locality that you broke in the Schwinger limit and somewhere else that it talks to,
And then where
based on the superpose. And believe it or not,
where does
quantum entanglement.
spin kind of, how does spin involved here?
Spin.
Yeah.
Oh. So in other words, you can accelerate either in spin or accelerate in vibration, depending on which is easier from an engineering point of view. As you well know, when you spin something, even surpassing 10 to the 4 RPM, it's very hard to do so and keep this thing. So again, you might choose vibration. I just chose to put in both spin and vibration because the mathematics is highly similar.
So
But from an engineering point of view, you'd want to go with
when you say
vibration.
spin, do you mean spin like literally spinning a thing, not like electric?
Around its own axis.
And this is interesting, right? There have been a number. There's a very common through line in a lot of alternate gravity manipulation approaches relating to either macroscopic spin vis-a-vis something called the POEMS theory, Pope-Osborne angular momentum synergy theory, something that Richard Eskridge looked into at Marshall, and then Alzafon's nucleonic spin approaches that he sort of scrubbed with Feynman back in the 30s.
Very complex, though.
Yeah. But then you've got Ming Lee's work with the rotating superconductor, the YBCO.
Also, Eugene Pokletnov used rotating superconductors, and I didn't realize this, but Nick Cook, who wrote The Hunt for Zero
Sure.
Point, he went,
Great book.
great book. He went up to Pokletnov,
Great
and
book.
they were speaking, and for whatever reason, Nick Cook had this instinct to ask him about Victor Schauberger, and somehow
Interesting. Yeah.
And Pokletnov goes, "Yeah, my father was this Soviet agent at the time, or he was a Russian agent.
Yeah.
This was like, he was Soviet. Yeah. He said, my father was a Soviet agent, and he was actually counterintel, and he was tasked with retrieving a lot of Schauberger's files. So Schauberger was one of the first people to talk about rotating, I think in his case, he had something called an impeller machine. This was pre kind of superconductivity.
Based on implosion rather than, right? The whole idea of creation, again, a physics based on creation rather than destruction.
Yeah.
Well, and do you think there's a
Yeah, but there was a connection between him
Absolutely.
and Pokletnov. And then Pokletov said, well, we just needed more higher RPMs.
But again, from an engineering point of view, you know how detrimental that can be.
It's very hard to do. It's a very
hard
exotic
to do. And
environment.
that's why I chose
What are you going to put in
vibration.
there? Yeah, sure.
And not just vibration of an electrically charged object, but plasma.
So you think that lineage doesn't make sense from an engineering standpoint? Actually, vibration makes more sense.
And you know why?
Yeah. I mean, because
Why?
with
Let's
plasmas,
listen to Jack. By the way, Jack is
Like an
brilliant.
idiot.
No, far from it. Jesse, please, 100%. That is totally unfair. Never, ever say that.
No, I mean, I'm just, you guys are more advanced than me. So
well, there's interesting things you can do when you set up standing waves in plasmas. I mean, you can generate cold plasmas, as he was talking about. This is something I did in my graduate research back in the day, with certain frequencies that will pull electrons off of the atoms, and then you can start doing interesting things with those electrons, and you can set up double layer plasmas and things like this. And if you can control where the charge goes, I mean, this is the problem with a lot of hot fusion experiments, is that they can't control where the electrons go, they can't control where the hot ions go, and so you get all kinds of breaking radiation, you get Bremsstrahlung, and you get all kinds of tremendous losses. And this approach ameliorates that.
So that's why you need cold plasma for the vibration.
It's ideal, yes.
Interesting. And how do you produce cold plasma? The fourth energy?
Not easy.
Right.
That is E cubed.
Okay, got it.
Absolutely, we'll not touch on that.
It's in the academic literature, but perhaps we don't verify it.
Since after all, this is my so-called first in-person interview.
Yeah.
So I should offer something to the audience. It involves something that has been given the Nobel Prize physics, Nobel Prize in physics. I believe it was last year.
Non-local reality, guys?
Lasers.
Interesting.
Leave it there.
So that's a better approach then. And then what does this have to do with superconductivity, I guess?
Believe it or not, everything is related at the quantum vacuum level.
So I'll throw something out there. So in superconducting physics, so we have this baseline theory called BCS theory.
Bardeen-Cooper.
Yeah. So Bardeen, brilliant physicist, two Nobel Prizes, the transistor and superconductivity. And so most superconductors, their behavior is characterized by BCS theory. However, these are typically ultra low temperature superconductors and extremely high B field superconductors. So these are not terribly useful in industrial commercial application because the environments you have to put them in are very exotic. So of course, superconductivity is very useful because it offers lossless power transmission, very high electric fields, very high magnetic fields. I've often said that the development and discovery of a room temperature superconductor is as transformative to commerce and industry as anti-gravity.
Very disruptive.
100%.
Extremely disruptive.
Now, so there's been a lot of research the last 30 or 40 years into topological materials, topological insulators, and then something called topological superconductors. And the nature of a topological material is, so typically you have crystal lattice materials. So metals are crystals, insulators are crystals, semiconductors are crystals. Ordinarily, those crystals have the same properties throughout the bulk of the matrix. Like no matter which way, frequently they're isotropic, meaning this way or that way, or they're anisotropic, meaning it's different this way versus that way. When you make semiconductor crystals, you get polycrystalline, so you get grain boundaries, and features stop at these grain boundaries, and so you start to get anisotropies. That's significant to manufacturing semiconductor materials, where we're doping these layers with different atoms, and we've been doping since the 1950s. I mean, this has been around some time, but the level of precision in semiconductor doping is 3 or 4 orders of magnitude lower than what we're talking about with these quantum heterostructured lattices, where you really need these big chromium and vanadium atoms that install their ferromagnetic ordering across the lattice. You need them in very specific lattice locations.
Jack, you're absolutely brilliant and right on. But let's bring it to a very simplistic, again, Occam's razor, simplicity and minimalism. What does superconductivity truly represent? A macroscopic quantum phenomenon.
Yes.
And it speaks directly to macroscopic quantum coherence. Look very carefully at slides 4 to 9 in the 2019 AIAA SciTech. A lot of people have gone over those slides as if there's nothing there. There's something of incredibly importance.
So how do you maintain coherence at macroscopic scales?
Not easy at all.
Condensates.
Because everything wants to decohere. Everything wants extremely cold temperatures. Again, the atoms being in this nice dance. Because of electron Coulomb repulsion, these things don't want to pair up, and yet BCS theory says that they should. And Dr. Victor Lachnau believes it's not the electrons but bipolarions. The whole idea of a bipolaron mechanism that occurs at these higher temperatures.
Which is a quasi-particle. It's a composite quasi-particle of 2 polarons. A polaron is itself a quasi-particle, which is...
And the Pais effect speaks directly to what? To this mechanism of room temperature superconductivity. How? It basically says once you form an alternating magnetic field, once you form this Bose-Einstein condensate that Victor Lachnau speaks to, you can use a pulse current, again, an alternate current, to move it.
To manipulate it.
Room temperature superconductivity. And yet no one has touched on either the Victor Lachnau paper or my patent.
How would
Thinking again, it's pseudoscience.
how would you do this?
So the reason generally you can't get superconductivity at high temperatures because the atoms in the material have all this thermal motion. They have all this thermal energy. And so the nature of superconductivity is that this thing called a phonon, which is a vibratory mode of an atom inside of a lattice, phonons facilitate the transfer of electrons through the lattice as Cooper pairs. So the Pauli exclusion principle only applies to spin 1/2 bosons. I know this is really deep, but what happens is when you force electrons close together, they behave as though they're a spin 1 particle, meaning Pauli no longer applies. And so they can both occupy the minimum ground state, so they can move together. So there's no degeneracy, there's no energy splitting. And so they move very efficiently through the lattice. Problem is, if this lattice is warm and all these atoms are vibrating randomly, you can't get this coherent phonon behavior. In extremely novelly comprised lattices, you put atoms in just the right place such that these internal magnetic fields set up these roadways, stop signs, highways for current to flow, and you can get this behavior.
So it would involve, you would need to fabricate materials on an atomic level. You need to get sub-inks.
But not the Pais effect. The Pais effect does not speak to anything depending on chemical composition. That's why Dr. Victor Lagno, he picked it up because he realized this is the solution to an active superconductor, one that's not passive, one that is not based on chemical composition,
So
like the type 1A or the type 2 superconductors. This is basically, it can be done as long as this thing at any point in its structure has been superconducting. For example, that's why I chose lead zirconate, titanate. All three components at very low temperatures are superconducting.
Sure.
And yet, because of the bipolar mechanism that Dr. Lagno, I believe, in his paper, it's just a 3-page paper, but on the 3rd page, he gives the mechanism and he speaks to the Pais effect, room temperatures for conductor. He believes it'll work.
So these materials are superconducting in their natural state, even at room temperature?
Not at room temperature, at
That's-
very low temperature.
He's describing conventional superconductors,
Right.
like YBCO and from
Lead zirconate, titanate, PbZr, Ti. These are the components of what they call a piezoelectric material.
You know, Townsend Brown spent the latter half of his career looking at piezoelectric material.
They're very important because one talks to, again, the whole idea that pressure induced what? The electric field can also induce pressure changes.
In the vacuum.
Well, I discovered something very interesting. The Townsend Brown ceramic insulator of choice was
It is
barium
interesting.
titanate.
It's on
It
the
is
chalkboard
very
in
interesting.
videos of him at
And yet they
Boston
have
Glass.
dismissed
This
his
is
work.
what changed my mind about
They have
Townsend Brown.
dismissed
It's
his
a
work.
Winter Haven.
Yeah.
And they have dismissed his work.
And
And
he
all the
says-
man is Charles